Okie dokie.
Okay, we can start. Welcome, everyone. Today's speaker for our extra colloquium is Dr. Julie Shetty, who got her master's in space science at UCL and then a PhD at Queen's in Belfast. And she's now an assistant professor at New Mexico State University, where she is the science lead and director for the Dunn Solar Telescope at Sunspot. Her research focuses on high cadence observations of the solar chromosphere, including jets, swirls, and practical flare nowcasting. And she is a co-author on the Sunspot Solar Observatory Data Archive Operations paper. Recent work includes the first high-resolution observations of chromospheric swirls from the Dunn. And she's visiting this week with an undergrad from New Mexico State, who is Eduardo Sanchez. So if they'll be here through the end of the week. So if you wanted to chat to either of them, come and say hi.
1.5 days left.
Yes.
And thanks, Paul, for a very nice intro. I'm very happy to come here. If you guys don't know me, some of you might know me, but I came here as a graduate student, then I came here as a postdoc, and I'm like almost every year, and then now I'm coming as a faculty. So it's been like a place where I do the next thing in my life. And I have been really kept busy by a lot of you guys visiting and talking to me. And I do have a dog who has come here, and maybe it's because of him that I don't have time to breathe when I'm here. A lot of you are talking. But thanks a lot. So before I start my, before the movie that you saw is actually from Matthias. Long time ago, when I was here as a student, this was their research in 2018. So student postdoc, I don't remember, but this was a movie that they played to me, not just for me, but for people a few years ago. And this is Mark Chung, Matthias Rampel, and a bunch of others who had done this movie that shows you how the flare is being formed and all the complexities that lead to the buildup and the eruption of the flare. So you're looking at a lot of these complications that you see and then the buildup. I like this movie because it has a lot of colors, and when I'm talking to people about this flare, they get excited because they see a lot of colors. But these kind of complexities that you see, sometimes we see them with the telescopes and we go like, wow, well, what's really going on? Okay, I don't know where my presentation went.
Your internet connection may have dropped.
Honest teacher, the dog ate my presentation.
Yes. I moved, but there are no wires, so he did not move any.
Are you still in the meeting, or did you get kicked out?
Oh,
I see.
Not part of the meeting. It looks like she's not part of the meeting.
Yeah.
You are. I can see you here, but I think you're still in the meeting, but your screen sharing somehow stopped.
So share window. Yeah, this window.
We should go back to share the whole screen instead of. Get a cookie.
Okay.
Let's try stop presenting and try again, sharing the screen rather than the window. Yeah.
That entire screen. I think we're back. I mean, it's very funny because Boulder moved, but he did not do anything. All right, we're back. So over the period of few years, I have built some collaborations. You can see HAO here, and so I would like to thank them whenever I start talking. for all the help that they have given me in designing my team. And this is the team. So a bunch of us, I just had my first graduate student passing last year, and she's now a postdoc, Juana. But you can see docs kind of in there. You know Eddie Eduardo Sanchez, who's here. But a bunch of other undergraduate students. So I started my own undergraduate student program, which trains students to study solar physics. So we do solar terrestrial relationships, and it's a combination of experiments and theory. That thing on the left top is actually a farm in New Mexico where we did some of our experiments because no one else could give us a site that did not have paperwork. So we do some crazy things. Bottom left is Kayla, who's an art major, and she's taken solar physics to different places around the city. And you're going to learn a little bit about the current research that I'm doing. But a bunch of grads, a bunch of undergrads. I'm in the process of hiring a new postdoc starting with me, Aparna. She's returning from Los Alamos. Yeah. Fun fact. Pre-Waldo, my team had 2 students and 1 faculty. That was me. Post-Waldo, we have 4 GAs, 6 undergraduates, 1 postdoc, and we're currently in the process of hiring another solar faculty. So, you know, those guys who are here, people who know something about budgeting, please budget a dog in your proposal if you want to like expand your team. And, you know, as you can see, he's a nice dog. Okay, another advertisement kind of a thing. So what we do at the Dunn, Dunn Solar Telescope was the first telescope I had ever seen in my life. Like, I mean, I had seen the small ones, but it was nothing like what I had seen as a child growing up with just looking at the telescope directly or putting a camera on the end. And this was in 2014 when I went there, and I was just mesmerized to continue working there. So we are still working there. We're still doing a lot of our observations. We designed a flare patrol program in 2019 that has led to a lot of the data that I'm talking about. And beyond just instrument development, we're developing new instrument like at this minute. Like there's a new instrument tested every few months, which is not like few days like it used to be. But the last one has been last week, which was a event camera system that we checked. But earlier in the year, we had Francis test run, and Francis is now working, which is a Queen's University Belfast instrument. And I also learned how to launch things on balloons while I was there. So we do send things, and Eddie here puts things on rockets and flies them. So when we're kind of expanding on the instrumentation side of things. As I said, so 2019 onwards, we have started collecting and curating flare data sets from Dunn. And when I'm saying collecting and curating, you know, you guys know that that you guys have been in part of some of these earlier pre-2019 data sets of flares. What I'm trying to do is also, if you have data sets, please send them to me. But what I'm trying to do is get them reduced in kind of a universal way. So we kind of know exactly what the parameters are from the data reduction point of view. And we can also calibrate them in such a way that we kind of more like STO, that we have like a systematic, you know, if you download the data, you know what it's showing and what are the seeing parameters, etc. So we are calibrating, quantifying them. When it comes to flare, we're also trying to figure out how we are observing them from pre-flare signatures to post-flare things that you'll see. And a lot of what I do is also to teach now, taking more of the teaching roles to talk to students like Eddie. I don't know if he's bored with me. I mean, he's just leaving, so probably. But I also, no one moves because this is, if anyone moves, I think this is kicking me off. Oh, hold on. No, it's not this. But now I have to sign back in.
If you keep having problems, you could send me the presentation and I can try on mine.
Okay.
My same problem yesterday.
Did you?
Constantly kicked out.
Okay. So it's not me, but no one moves. I think it stinks. I mean, share screen. Share entire screen. So a lot of what I'm doing is also figuring out how children in New Mexico are learning about our space. I won't talk about that. But there are some unique things that I find when I take solar physics to those kids around. So what are we expecting today? We're expecting what a solar flare is, and a lot, but I want to really focus on some of the current research that is coming out. And I'm saying current, this is developing the last few months. And also, so we submitted some papers we're building up. Yep. So what is a solar flare? It's a sudden impulsive release of energy or emission that you see. It produces hot plasma like features that you see here. And usually we see that in soft X-rays radio, but we also see that in visible line, but not as dramatic as you see here. So these are the flashes that we know of the flare to be. The eruptions usually last from minutes to hours. The whole buildup might be days. Some of these eruptions, when I'm talking about flares to people, I usually talk about, these are eruptions that are on the sound that not all our technology of. Different classes of flares, we know the A, B, C, and X. What we really see at the Dunn are C, M, and X class flares, and usually kind of the bigger size flares. And the one that I showed you here was X class flare that happened 2 days ago. So it wasn't unfortunately captured at the Dunn, but we did catch some C class flares that led to it. So phases of flares, and why it is important is when we curate the flare data sets from Dunn, we are kind of seeing new things that are happening even to trigger the flares, and also what is happening after the flare has happened. So we know generally we could have multiple phases of flares. So I'm talking about like breaking things into kind of four phases of flares. So first phase is basically where does the flare happen? So for the flare to happen, especially an X-class flare to happen, you're looking at complex magnetic fields. Okay? So you're looking at structures here, and I'm pointing at delta structure where you have like opposite polarity sunspots kind of overlapping each other. And this is a cool movie that I found was simple enough on internet. And you can see like a magnetic arcade and then the delta sunspot kind of adding into the complexity, and you can start seeing some field lines breaking up. As a very simplified way of how a flare might be triggered. So first thing that we're looking at is complex magnetic fields. And now we have instrument called spinner at Dunn that can actually tell you about what is going on in terms of magnetic field. Okay? The second phase of flare is usually these sparkles or emissions, technically. And this is the impulsive phase where we see rapid energy release, usually because of different types of magnetic reconnections. In this case, this was an X-class flare. And what we're looking at Dunn is basically the calcium and H-alpha, the chromospheric build up to this kind of eruption. Okay? Then you have the final phase, which is technically the final phase, which is the decay phase. You usually see this is after you have the emission, and this decay phase kind of continues for another few hours sometimes. And when you look at stars like I have here, you start seeing these oscillations and you start seeing these quasi-periodic pulsations in some of these flares. So usually here, you'll start seeing flare ribbons kind of separate out, fade. You don't see brightenings, bright structures in the images anymore at this time, and everything seems to kind of cool down. Depending on the size and the scale of the eruption, this continues. So this is like a standard picture of flare that we know. And what we're trying to do at Dunn, which is kind of interesting coming from like being an old legacy telescope, is we start seeing new things. And I'm going to just like reshare. So. And that has not worked again. Is there a way like I can screen share into your laptop or something?
I don't know if you could screen share into my laptop, but you could send me the presentation and I could try and share it.
I'm thinking let me do it this way. So you have the whole keynote and we could just do it. AirDrop?
It should work. And that here.
I need to turn your book on somewhere to get it.
Go to Finder and open an AirDrop window, I think.
And if you switch on the Bluetooth, it will be.
Yeah, so she should be able to, yeah,
Yeah, okay.
you can send it to you.
I'm not able to find it.
Yeah, sorry, I had to allow that.
Okay.
Should be able to do it now.
Is it HAO setter?
Yeah, I got it.
Okay. Is it working?
Yeah, it's just downloading. Give it one more second.
We're recording like silence.
What's the future of the Dunn?
Good question.
Yeah, I don't answer that. Keep talking.
Well,
If I ask the question, it might prompt it to start working.
it's now in full screen, so it's okay. It could be, I think we leave it here.
You can just advance it yourself.
Okay. Okay. Also,
Oh,
so
same problem.
I think so. You have to break divide it, right? So.
It's quasi-periodic talk I've ever seen. It's every 5 minutes or so that it shuts down, you know.
I think anyone moves, no one moves, except probably I should sit down. Hey, there was a geomagnetic storm, right? I did give a talk like this, and then something happened, and there was a geomagnetic storm. It wasn't affecting the talk, but I had like a loose connection at the start of the term, which is very cute. Okay, so we see these decay phases where things are relaxing. Yeah? So when it flares, we try to capture it at the dawn. And if I ask ChatGPT to figure out what we do, that's what he comes up with. So we're kind of pointing at the sun and a bunch of messages sitting around. This is where I was talking about the data archive. So what we have, as I said, was like curated data sets, bunch of these since 2019, and we just had our data release. And in that data release, you can see that we've observed different things. So we have more than 200 active region data sets. Physically impossible for me to study all of them, or my 10-person team. But we have 200 odd active region data sets, filaments, another 320, mainly those that are giving rise to flares. So we have a bunch of 500 data sets, and they're all in a good shape. When I'm talking about good shape, they're all like level 1 or level 2. So some of them you can just download and start analyzing the data. And but in the first few years where we had IDIS, most of them are still having HART-CAN, ROSA, and a bunch of our new magnetic field kind of spectropolarimeters, spinor and bars. And so there is a lot of like data that is not just fancy images, but also magnetic field information. This movie here is how the Dunn Solar Telescope is still able to resolve some of these images when it comes to comparing with HMI and STO. So you're going through different ROSA channels at the Dunn, and this is a 2025 observation. And you can see the kind of image stability, etc. It's kind of still there.
Which line is that?
So we went from the photosphere, which was G band, to calcium K and H alpha. So this one is calcium K.
Calcium K is that's really good. I mean, that's hard to get because of the seeing diffraction, differential refraction and all that. And
Yes.
in that blue part of the spectrum, I mean.
I agree, and so it's really being interesting to see that Dunn is still able to do this. And then we not only do we know how to get the calcium K, the number of photons that we need to create this kind of data set, we also have like a standard, like, so we know what to do now. And it's interesting because I'm going to focus a lot of my talk on calcium K.
Those are data.
Yes. So this is G-band. So obviously when it comes to TIO and BBI, it's not as amazing, but we are able to resolve your supergranules and granules and stuff like that. And then this is calcium K. And I really like this line now because it's showing me, this is kind of a flare image, and it's kind of showing me all these jets that I like to see. And then this is H alpha for the same image. And yes, so the crispiness of this data set is what I really like. And the fact that we have 200 odd data sets that are like that, with active regions doing the random things. It's very interesting. I really like the jets that you see here too. That's why I started looking into this data set. And so, having showed you that scan of images, we use that as our first understanding of flaring regions. So this is all systematically done using visual eyes. So what we have is, we are right now building a 50+ flare catalog, where you would see such data sets that are already level 2 and already showing you a lot of like detailed features of the flare that I showed in the movie in the first slide, because you could see like different jets that are going on. You could see how the plasma is moving around and turning around, and you really can investigate some of these things. What is also interesting is since 2025, and Robertus is not here because he helped prepare the spinner instrument to get very high cadence spectropolarimetric observations. So we can take spectropolarimetric observations in 2 wavelength positions using spinner, and we can do that in 30 seconds. So you get the full spectral line information. You have your image at the foot points of these light bridges or polarity inversion lines, and you get the full Stokes values that you need to invert the data. And so, of course, the whole inversion takes ages, but it's there, and yeah, it's pretty much a data set that we are still investigating. Okay. So my first talk, I'm going to talk about what I see in some of these calcium images. And the resolution in this image is not very good, but what I see is in multiple of flares, I see these brightenings that happen, and I'm going to go through a movie in a second. These brightenings occur around 20 minutes to 30 minutes before I see a flare in GOES. Okay? So here are some light curves. The region 2 is here, which is the flare, and region 3 that is here, and you have a sunspot with the umbral kind of connection. So there's like a umbral light bridge going on here, and these 2 regions seem to be connected, and whatever I see first happens here. So you start seeing brightening, calcium K brightening, and then that tends to trigger something here, which triggers a big flare. So you're looking at light curves here. First, bottom one is flare light curve, where we actually see this blue curve that shows you like kind of calcium K data in this region. And then in region 3, we have the brightening light curve, which kind of brightens before. And then we've overplotted GOES to kind of show us that where the GOES C-class flare occurred. So the brightening of the flare is kind of matching with the GOES light curve. And then the trigger region, which is the brightening region, it predates. It occurs before, and like somewhere around 30 minutes before the main flare is happening. And then it kind of peaks up again, sometimes to the same level. So we see this surge, then dip motif that I see in not just one event, but multiple events using this data. Okay. So here's a data that I have been investigating in great details. When I'm saying great details, this is, I mean, we're trying to figure out everything that is happening here. Okay. So first, I will start with here. So this was a AIA region, but here is your calcium K image. You saw a zoomed in view earlier. So this is a movie, and I'm going to focus a lot on this part, and then we're going to look into this part, and I'm going to spend some time in this movie, and this should be pretty much automatic, but let's go back. So here's my brightening. Okay? So this is where I start seeing brightening that is going on, and I start seeing these jets. And this has been my career, so I stop here. But then I started looking at something happening here. So this brightening has happened, and that there seems to be bright structures around here, and then around here. And so when I was looking at it, I was looking at it from point of view of the jets. But then you kind of see flare ribbons and put things together in a second here. And then once you start seeing the flare, the whole flare behavior has kind of whitened out a little bit now. And then you will start seeing stuff brightening back here. So you kind of see a surge and dip motif that seems to be connected to the flare. To see the actual connection, I do 2 things. The first thing is, as someone who studied the chromosphere, we want to see if there are fibrils that are connected. Okay? So here you are going to see a U-shaped fibril, like it's kind of a V like that is connected. And then you see jet activity. And at some point, this disappears. So that's where it has disappeared. So this kind of fibril that was connecting the flare disappeared, and then it triggered the flare. And then you start seeing the whole flare ribbon set up. You can zoom into, and you can see all the different parts of the flare that are happening. So this is, the good thing is this is a C-class flare, so relatively easier magnetic configuration to investigate, but also detailed enough to tell me a little bit more about what is going on in these triggers. Okay, so even with like kind of two evidences put together, I'm kind of in a pseudoscience way trying to figure out if this is actually happening. And then we kind of did such analysis on 8 other flares that kind of showed there were different aspects of calcium K brightenings that occurred before the main flare occurred. Okay? The big question is, why is this site triggering the flare and not any other site in this, right? So we don't see the same behavior if I take this calcium brightening, for example. Okay? So it's easy to look into 8 flares and find the exact connections of how the fibrils are connected, and then put up some kind of sequential images to see how the jets are getting developed, and how the jet shape is kind of connecting to the flare. Right now, everything seems physically what you guys know about flares, and then when I put this together, you get this kind of an idea of what is happening. But we kind of kept on seeing this in multiple flares, and then we also started seeing that their H-alpha signatures were related. Okay? So we did this, and then we have a paper that we are talking about where we talk about not only the chromospheric connection, but also looking at magnetic fields from the spinner. So this was not possible before Robertus came and fixed the instrument earlier. So shame to not have him in the audience. Mind you, the images are flipped, but it's the same image. And you can see here is the main polarity inversion line where you actually see the main flare happening. And the jets kind of occur around here. And the flare ribbon is somewhere here. Okay? So the other end of the flare. So you kind of see it flipped. I did not correct the images before I put them in the video, but these kind of are the same thing. And then you can see basically with this spectral scan that we were looking at a complex magnetic field structure at the photosphere. And now I'll just show you what we see at the chromosphere. In the chromosphere too, we are able to build these signals together, and we are able to show that the magnetic field lines are kind of very complex where this flaring is occurring. And what we don't understand yet is if they are connected, right? So that is the big thing, if the jet sites and the flare sites are kind of connected. But what I'm also trying to show you is we are able to get a chromospheric only signature of flare to understand actually what is happening in the ribbons, the flaring ribbons that we see. All right, so once we know that, using spinner data, a very quick thing that I can do is we can build a 2-dimensional magnetic toy model. When I'm saying toy, it's really not that toy. It has some physics around it. This was dynamic Longcock's technique that I have modified for spinner. And here what I have is the different sites. So I have the flare foot points, the jet foot points. First 1, 2 are my jet foot points, and then 3, 4, and 5 is where we have flares. Yeah? The system is a very simple equation. It's just on distance of how these field lines should occur. And then from one field line, one kind of foot point kind of send field lines to the next foot point, and they both have to be different polarities. So basically positive to negative reconnection. Oh, connection, not reconnection. So based on that, what I have here is I have the first two regions that are the jet foot points connecting to flare foot points. So we do see this connection occurring in the Stokes. When we translate the Stokes data into something meaningful. And then what was interesting for me is there were two scans that we did with Spinner, and this were like 10-minute scans. So the first scan was kind of pre-flare, and the second scan was post-flare. And the magnetic field did change enough that when I ran the same algorithm, I kind of got two different configurations. Okay? So in the first configuration, I see that the jets are kind of continuously connected to the flare foot point that was close by, which is 4. And sometimes we also see some connections from 5, which is where the other end of the ribbon happened to the jets. But after the flare had happened, all these foot points kind of, the flaring regions kind of just go away. They don't reconnect necessarily to 1 and 2. And most of the magnetic field that is going from 1 and 2 is going to 3 rather than anything else. And so this magnetic extrapolation tells me the second proof that I want, that is to show how these events are kind of connected. Okay, so we're further studying this in kind of inverting the data. And we are also trying to understand how energy is being transferred after we get the inversion parameters, and we use Hazel to invert it. Yeah. So do we see this in other data sets? I stopped at 2 and I gave my work to my student to continue. So Aman's leading this work, and we've just submitted it. And so we see that there is a difference between when peaks are observed, and the difference is somewhere around like 19 minutes to 40 minutes. That's the total difference between the peaks. And we kept on seeing this. So, of course, this 8 sets of data sets is not 8 out of 214. We haven't finished looking at all the 214 that I just said. And this is where I have stopped using human eyes. And now I'm trying to train neural networks to kind of identify this behavior based on a tracking algorithm that I built with a student a few years ago. And then what we're trying to do is to see how the jet sites are also connected to the flaring sites, but also in the data set, which of these brightenings that occur around sunspot are leading to these kind of connections. Yeah? So that's where it goes to the neural network. We have 1 million images. Okay. What was also interesting is I started looking at some data that I had studied during my PhD, and I had looked into different stars and light curves of different stars. So this is a very simplified result that I had just produced on Monday. So I was here when I did this. So I looked into TIS 4114 20236 light curve. I honestly don't know what they mean. I just know that TESS is a satellite that studies flaring stars. And if I use this keyword and in my Python script, it will download the light curve. I don't have information about its pointing or what it's doing or what the science plan was. So there's a lot of data available. So there is a lot of stars from Kepler and TESS that show you have your superflares. Okay? So the pink ones that I have identified are superflares, and the orange ones that are here are the pre-flare precursors that I see in this channel. And this is optical wavelength, but it's not narrowband for what we're looking at. So it's kind of the whole visible light spectrum that's there. But you do see multiple locations in a star like this, which is a G-type star that has a lot of superflares. you do see multiple smaller flares. Yeah. And there is some distance, time difference between them. Of course, the time difference is more even around 500 minutes rather than 30 minutes. But this was just one star that I studied in details. And when I'm saying details, kind of started identifying these things. And I repeated the same method to 30 other stars. And now I have more than 1,000 search dip pairs. And so it seems like other flaring stars also hint to a smaller flare before a super flare happens. Again, this is not something new. What is interesting is that we can again go back to an MSU and we have some toy telescopes and hydrogen and calcium filters that we can put in to investigate if this is kind of happening in those lines. And that's kind of the next thing that I'm trying to figure out.
How bright are those stars?
So,
Pretty dim, I would think.
so the flux, yes, they are going to be very dim, but the flux, I'm more interested in like the flux increase. And then you can quantify the flux increase. Like in this case, like the flux increases from 2600 to 28,500, 28,500. So there's a lot of flux increase. But any flux increase beyond 50 quantity photons or the total flux that you get at the detector, I can say that that is a reasonable guess that there is some science in it and that's not noise. So they are going to be faint, but we can technically resolve these stars.
So you would use narrowband filters, not a spectrograph?
So the big thing, I know that APO, I could easily put a filter, but then I have to go to STSW to do a spectral analysis. And then I don't know how fast spectral analysis will work, and also more competition. So instead of writing another like observing campaign for STSs, I'm just using current filters that we have and use a smaller telescope to actually see if this works. And so
All the telescopes are 14-inch or something.
24-inch.
Oh, that's not a small telescope. That's a search telescope, yeah.
She's got a whole freaking big telescope. It's a small telescope to what she's got, right?
20 minutes, not 20, okay, 20 minutes is too well. Like we have Totegas Mountain Observatory on the campus where we can do this thing. It's a challenge, but we can easily do this. And students like Eddie can.
Yeah,
Good.
all telescopes like this, I mean, they're ideal for education, but I think there's a strong scientific motivation that
Yeah.
you can't get time on the big telescopes and you can do this kind of work on the small one.
Yeah, it's in the backyard, right?
It's a really nice way to do it.
And then we have the filters already on. Like, do you want calcium K at this wavelength or this wavelength? Or like,
Yeah.
okay, maybe we could. We already have abundant filters, so I can easily do those. And so I want to continue the study to see actually the stellar flares, if we have these 30 candidates that I've looked into, if they can be observed, and then, if they can tell us more about these precursors, because it becoming a time where it is more like using more machine learning or automated detection codes. So my last few minutes, I'm going to talk about Eddie's work. And so I mentioned 3 phases of solar flares. And so there is actually a 4th flare. Unfortunately, I don't have your tornado one. So there are actually fourth phase that happens. And this is kind of a secondary peak that occurs after a flare has happened. Okay? So it's talking about the pre-flare signatures, and I'm turning the page a little bit and talking about the post-flare signatures again. So some of these, as you see here, are like secondary peaks in EUV lines. And there's been a report about this. Multiple people have reported this. So you get a flare, and instead of just falling down, the decay, it kind of peaks goes through a second peak. And this is almost like a phase that kind of never shows up, but sometimes it shows up. And so we were interested in looking at our X-class flare that we had observed that this should be a movie. And so this movie is actually made by Eddie here. And so we captured the flare, and then we looked into the continuous activity that we see after the flare has occurred. And then I think I don't unfortunately have the DST data that Eddie has analyzed. But we see something that I want to focus on, and I think I can do with the 3 or 4 one. So why Eddie was interested in looking at this, one, it was an X-class flare, but here, after the flare has occurred, you start seeing like a reconnection, a release of energy, but that kind of turns into a tornado. So one of the first things that Eddie was looking at is
that
how-
1420?
Oh, okay.
Mhm.
Thanks. Oops. Let's stop there, actually. Right. So you see this tornado, okay? Now, from chromosphere point of view, I'm interested in doing these tornadoes. So this flare, after it has finished its post-flare evolution, it still has these complex magnetic shenanigans that it's doing, and it's creating these tornadoes and multiple different types of flares that we see in this DCAR. Okay. So here you have the tornado kind of ripping, breaking and ripping apart, which is again like similar to asymmetric flare eruptions, loop eruptions. It's nothing new. We are just kind of looking into understanding what is triggering it. So while he was doing that, we started looking into like multiple regions. So it came up with like the final number 12 or 16, but like in this image, it's like 12 region of interest. We did the same thing. We started looking at the light curves. So you have region 12, that is a quiet sun understanding, like nothing is going on. Region 2 was where you saw the tornado. And multiple other regions around the sunspot that we started looking into. And now we stopped looking into tornado anymore because region 1 and 9, I'm going to show only one in details, 1, 9, and I think even 8, they kind of create a different flare that follows up. So you saw the first flare, or you did not see the first flare, declining part of the first flare. But when you put a light curve, region 1, which is here on the other side of the sunspot, started showing a flare-like peak. Okay? You can sometimes see it in region 3, you can see it in region 4. But many times when you see it, you kind of see it as a jet activity. But we see it in region 1 as an isolated peak. So it looks like there's a secondary flare that was triggered by the first flare. And we see that on region 9. I don't have region 9 with me. But when I put things together, we kind of see the declining phase. And then we see this secondary phase. So the word that we investigated and we came up with serial flaring. So like it's basically a sequence of 2 or more flares that occur from kind of the same activation, but after the first flare. And these serial flares are not detected by GOES. They are not like the secondary UV bursts that you see. We do see them in 171. We do see them in 3 or 4, but we also see them a lot in calcium K line, which is the light blue one, and the H alpha line. So they seem to be chromospheric material that does reach higher temperatures, but we don't see that in kind of GOES. Okay, and so this basically occurs from the same flare, and then it occurs at very short time scales, so minutes to a few hours apart from the first peak. And they're happening in the same kind of magnetic region. And if I go back, okay, I think this one, the next one. So it's basically this sunspot group that kind of created the main X-class flare, and that led to these serial flares. And if Eddie was not here, he probably finished this paper up and then would have submitted it by this week. So I'm trying to get Eddie to submit this week. Why this is interesting is because these kind of serial flaring, you always see sympathetic flares where you have the first flare happening and then the second flare happening after the first flare has kind of finished its life cycle. But this is happening while we are in the declining phase. And we kind of find almost like 2 or 3 papers talking about this, but almost none talking about the chromospheric response that again we see from the calcium K and H alpha lines. So I'm kind of selling these points that we see a lot of this in the chromosphere. And it's very different from the quasi-periodic pulsations that I showed in the decay phase of the previous examples that we have. So if it was a quasi-periodic pulsation, you would kind of see the pulse kind of going down, like maybe just systematic. This peak that I see, it's very much like an impulsive behavior that if I define what a flare is, I kind of see this impulsiveness, and then we call this a flare because of the shape of the light curve and also what we kind of see happening around. Unfortunately, I don't have updated images that Eddie has sent me that continues into this. But if you want to know more about serial flares and what have happened and how the chromosphere is responding, I'll just say catch Eddie because he's here. And he did send me everything, but I did not put it up in my slide on time. Okay, so what I have in total is basically the highlight is that these high cadence chromospheric images that I get from Dunn with the improved spinner instrument, they're kind of showing us new things about flares. And the beauty of that is all the data has been curated. And then every time I look at something is something new that I can't understand. And sometimes we have it in the theory, sometimes we don't have enough observational evidences. And main thing is if we get a strong pre-flare signature that we see in calcium images that we can use that information as a nowcasting tool. So change all the H alpha telescopes all around the world, like Gong to calcium K. So, giving an example of like really exploring that wavelength, because that seems to be a wavelength that we haven't really explored enough. I don't know why that is. And maybe it's because people did not think that was interesting. And as like Phil says, that to get a good images, to get good data from the bluer side of the spectrum is a little bit more challenging. And then basically what we want to use this data at the Dunn is to give like a consistent picture of how magnetic energy is stored, released, and redistributed amongst these flares. Unfortunately, with the 50 flares that we have 30 odd good data sets, and many of them show us new things rather than confirming what we have seen in the previous one. And it's not just a line of sight issue, it's also all the dynamics that we see might be different. So maybe each flare is a very different type of a flare. It has its own fingerprints that we don't know. And that's something that we are trying to explore. I'll finish my talk with these flares that happened this week. Bunch of complex magnetic sunspots that give rise to a lot of eruptions. But I'm happy to answer questions.
Thank you. So we have another meeting starting in this room in 1 minute time, but we do have time for maybe a couple of questions.
Okay.
Maybe I can start. So Larissa Krishna has written a few papers on this precursor brightenings that she sees in EUV images. I think she uses SUVI GOES rather than AIA. And she sees these brightenings, I think, an hour up to maybe 6 hours pre-flare. And I'm just wondering how the chromospheric brightness relate to that. Or have you looked at this? Are these the same regions that are doing the brightening, or is it unrelated, or how
So,
do they
I
compare?
have no guarantee to say that it's the same event,
Mhm.
and that's the challenging part, because with these images that I showed you, we have like 1 to 2 hours of like, observations that we can curate and make them science ready. So it's always a challenge to like see the 6 hour lag and stuff like that. We do know that a lot of these kind of coincide with what is going on in 304 and 171, but I haven't like explored like those SUVI channels. We are doing coordinated campaigns with Aditya, which looks into NUV, and that is also showing some interesting stuff there, because they're able to like right now resolve what a flare would look like. And so that would be potentially more matching with the goals, like with the CAK images that we have.
Anyone else?
Just
Yeah.
question regarding these secondary brightenings you see in some of the UV lines. Could you get something like this in principle also if the initial flare produced plasma with temperatures way above the typical UV lines, and then you see a secondary peak when this very hot plasma cools down enough that it again shows up in UV lines?
That's a good point. We haven't investigated it. Like Eddie was doing the DEM analysis to get the temperatures and see how the temperatures are changing. So that's the kind of like, understanding hotter to cooler plasma relationship. But I have not seen it on the lines of like even figuring it out if this occurs when, something else, like for example, if it is happening in M-class flare, not happening in M-class flare, it's only happening in X-class flare. That flare that I showed is X1. So it wasn't like the hottest X-class flare, right? So it was still X1. So unfortunately, we did not observe this one, the X5 that happened. So, just lost I think it happened a few hours before we could go on the sun, which is usually the story of everything that happened. But it's worth exploring, and also the magnetic field part of like really the energy buildup. That data is not having spinner, but with spinner we can get those things in chromospheric points. So we can build something in terms of understanding how the changes. But okay, I better get going.
Okay, thank you.
Thanks a lot. But I'm here, and if you have more